Hello everyone, we're about to start. So yep, welcome to the Prague Postgres Meetup once again. Cursor's on the wrong page. So yeah, thanks to Betsys for hosting and Alessia and Susanna for organizing everything. This place is pretty cool. So here's the agenda. We're going to first start off with advantages of Postgres by Chris. And then we're going to look at full text search by Alesh. And then we're going to have some talking to everybody. So yeah, and there's also some upcoming conferences. There's the called P2D2, the Postgres Developer Day. So you can check it out at the p2d2.cz. That's pretty cool. It's in the university, the Czech Technical University. And then there's also some workshops in the previous day. And then also like to remember Simon Riggs, who developed or helped develop many features that we take for granted these days. And yeah, a very unfortunate, untimely passing. So yeah, that's it.
Okay, right, first off, I brought some little gifts of some electric elephants. If anybody wants them, please take them. They kind of light up and flash. And thank you for kind of inviting me, or thank you to Gulchin for inviting me to come and speak to you. So first off, who am I? Well, I'm Chris. I'm based in the UK, if it isn't obvious from the t-shirt. And I kind of tend to go and call myself a bit of like IT jack of all trades. And kind of that's reflected a little bit in all the various different projects I've worked across in my kind of career. And I kind of have been using Postgres for around 18 odd years now at this point. So I think I've started on something like version 8 roughly. And this kind of talk is a bit of a like assembly of a lot of things across those projects that were useful and interesting. And bits of it originally were part of my talk on Internet of Things. And I figured a lot of the feedback from that was like it was a good walk through the features of Postgres. So that's kind of where this talk kind of comes from. And so at times we do dip in and out of lots of different examples if stuff doesn't always feel very joined up. And I think it's fair to say I kind of love Postgres. Been using it a long time, and it's a big passion of mine. Been to FOSDEM a few times. I helped kind of run the stall and stuff this year. I help organise the UK conference and help organise the PGConf EU this year and things like that. And I think it's fair to say across a lot of my career and projects, Postgres has kind of been a big advantage and a big positive in those projects being successful. And a lot of the times, like whilst there are some downsides to Postgres, it's always been like a net positive. And this kind of talk is much more geared towards application developers, people who are a little bit curious, right? And they want to go and find out all the different things that Postgres can do and what they can kind of use it for. It's not really, running big things at scale is difficult and hard regardless of the technology you choose. So this is much more about being practical, trying to actually make the best use of kind of what you're already using in your application. And kind of with that perspective, an often retort is, well, use the right tool for the job. Well, if you're kind of a small team, it's kind of a lot easier to understand 3 products well than it is to try and understand 10 different technologies. And I'm kind of like structured this talk a little bit in that we start off with like application architecture and potentially ways you can simplify that into like how you can maybe simplify data modeling and use kind of Postgres' advanced data types, and then into actually using Postgres to solve your kind of problems. So how many people work with application architectures that look a bit like this, with a whole mass of different technologies in the mix? Well, I'm kind of mainly here to say, just use Postgres, right? You don't need any of this stuff, right? Just use Postgres. And I think a fairly obvious starting point would be queues. So like they're a pretty common use case in lots of different applications. And loads of people probably immediately jump to something like Kafka or RabbitMQ, which they're not terrible solutions, right? But they can be very difficult to run at times, and it all depends on what you're doing. If you're just effectively needing one server with one little database, why do you want all the hassle of running that as well? And often I think kind of like we don't need to overthink this. A queue literally can just be that, a table with nothing more than a kind of status of some kind of payload when you inserted it and processed it. And all we need to do is just store that kind of payload in a row, and this is where like Postgres' call data types start coming helpful. Just store it as text if it's just a text or JSON, right? If it's JSON, we can use like fancy stuff like JSONB. Or, maybe it's some weird Java serialization stuff and you use binary data type. But again, right, the whole point is we don't really need to overthink this a lot of the time, so keep it simple. And now we can start introducing some of Postgres' smarts. So obviously, all we just want to do is query from our very simple table to find some records that we've not processed. So that's quite straightforward. We can use the status column to capture retries. So anything less than 4 times is kind of what we want to process. And we just want to order it kind of reverse order by time. And then we're going to pick a batch size of 10. But the real magic comes from for update skip locked. Who knows for update? One person? 2? A couple? So for update is really handy at being able to say, like, whilst I'm reading that row, obtain a lock on it as if I was going to update that record, which is effectively going to say, I'm going to stop any other transaction from being able to touch that record. But skip locked is where this becomes much more useful, in that whilst we try and grab 10 rows, if any of them are locked, we just keep going. So with those 4 keywords, we've effectively built a concurrency safe multi-consumer in Postgres that's all ACID compliant, right? I mean, it's actually quite difficult to do that in some of the queuing platforms. And it took us one table and a couple of lines of SQL. And that's kind of really like some of the advantages here of Postgres. And obviously, we care about performance as well, right? So we can use another cool feature of Postgres called partial indexes. So obviously, we only really care about records that we want to process. So we can just create an index only on those records. So in Postgres, when you create an index, you can specify a predicate as a where query, where clause. And that will basically say only index stuff that's currently in the state I want to use. So we're going to trade off a little bit more index maintenance here, but we can kind of keep things simple. And there's a few other little tricks we can play in this. Like we don't need a primary key necessarily, because for the particular use case here, we can use Postgres' internal like primary key of each record, which is called CTID. It's not quite a primary key, but if you're careful how you use it, you don't necessarily always need a primary key on everything. Save an extra column. So very simple walkthrough in how to do queuing. So, and obviously with that kind of nice index, when we do our query, we get a very simple index scan, nice and efficient, performant, nice and simple. And then kind of next big architectural kind of thing I want to talk about is text search. And I know Ellis is talking about this, so I don't want to take away from it. So I've deliberately cut this down a bit. And most people, so for example, another application I worked on, we'd got, like searching wasn't the primary use case, right? We just want to be able to administratively go and search across different entities in the database, stuff that's got a description, right? So this was a monitoring platform, we got a list of hosts, we got a description on all of them, just want to be able to quickly search it. I don't really want to go and spend the time of pushing all this into Elasticsearch, because that requires big, long ETL processes that routinely break. They're an absolute nightmare to work with. I've worked in so many applications and systems where they ETL'd their primary database into Elasticsearch, and it went over like every month, 3 days of downtime routinely. So we can just do it in Postgres. And a really simple way to just tack it on in Postgres is to use expression indexes. So Postgres has got full text search data types. So we have a data type called TS vector, which is a text search vector, which basically just stores the individual terms of the text and how many times they occur and where they occur. And so we can just use this directly in an index. We don't have to add a column or anything. And then as long as we use the same expression when we query it, which again is really easy, we just use Postgres's customized operators, we can just query our table in a full text way without having to necessarily even modify our schema. And I'm sure Ellis will talk a lot more about the not complicated part of it and nitty-gritty. And then I think the next big kind of architectural thing you can use Postgres to simplify would be kind of geospatial information. So quite a lot of stuff these days has some kind of location associated with it. And Postgres has got a really great extension called PostGIS, which is a full geographic extension. So it's as capable as Esri's, Arc, SDE extensions to Oracle, etc. And it's free. So there's obviously loads of situations where you don't need like all the powers of a full GIS system. You don't have all the data, but you can still do kind of simple use cases. So a good example of this was a booking app I had where every venue has a location. We know that. It's a fairly straightforward, just GPS coordinate. And HTML5 these days has a geolocation API. So it's really easy on a mobile phone, even without an app, to ask the user where they are. So we know 2 spatial points. So rather than having to go and use a third-party Google Maps API or anything like that, we can just do all of that in Postgres with one very simple query called std within, which does a distance within search. So we search for all the venues where the location is within 2 kilometers of my location. And another great thing with Postgres, again, advanced indexes and pluggable indexes, we can index accelerate that lookup. So we're not going to do a brute force table scan across all of that data. We can just do a very simple bounding box search that's all indexed using kind of R trees in Postgres. So that's at least 3 different systems I've cut out from your application architecture. And you really want to use Postgres now, right? And I think, if you're maybe more used to other kind of SQL databases, then I think Postgres' kind of fairly bewildering level of advanced data types kind of is another huge advantage. And I often find that I think how I kind of model data has changed over the years as Postgres has added more and more features. And the first one I'm going to start and talk about are arrays. So Postgres supports the concept of having an array of pretty much any data type that's defined. So be it an actual primitive data type built in, or an kind of complex data type, or even a data type from an extension, you can still create an array of them. And a really simple use case of this would be tags. So again, another thing that's really common in modern application development is kind of the ability to filter things by arbitrary tags. So let users put arbitrary tags on stuff and then query and filter by them. So I think the more SQL-y way to do this would be to have a table of tags and then a linked table for every entity you want to filter by. But I think it's much easier just to stick a text array on your entity, and then we can use the contains operator to do a very simple find me all records that have this tag on them. And again, cool indexes allow us to index accelerate that. So Gin can do a index accelerated contains lookup on arrays. So we don't even have to worry about performance of this method. It's probably on par with any other more kind of normalized method you could do. And another really big advantage of kind of arrays and this kind of approach is for what I call like data rollups. So a application I worked on for a long time was energy analytics. So we used to take in all of the energy read data from a large British gas supplier. And that would give us people's readings of every day, but also it gave people's energy readings of every 30 minutes. So that's quite a lot of data points. We don't really want to store 30 minutes across, we don't want to store 48 records for each day of energy usage. And a really good solution to this is instead we just roll it up into an array. So we store one record with an array of 48 elements. Because we're never going to query for what was somebody's energy usage at 12:30 on Monday. We're much more interested in saying what's people's energy usage for Monday and then viewing the whole thing. This is also another situation where breaking the golden rule of always using UTC time doesn't make any sense, and actually storing local time makes way more sense in this particular use case. And a massive advantage of this is underlying in Postgres, there's something called every tuple, every row has a header. And that typically uses 23 bytes. So in most IoT platforms, you're only storing like about 32 bytes of data. So your row overhead is pretty much 50-50 with your actual data. So if we instead store 48 data points into one array, we get a much better and more efficient use of our table space than wasting effectively 50% of the table space on just storing meta information that Postgres needs internally to do transaction control. So these kind of like techniques and apply to lots of different use cases as well. You can probably use it for like web analytics, all that kind of stuff. But it's actually also much more efficient under the hood in terms of not wasting your disk space. And I think it's also important to point out, like with power and great responsibility comes, the responsibility not to abuse it. And there's definitely been times where I probably went a bit over the top and a bit overboard. So I went through one phase of liking arrays quite a lot, and I thought I'd use them effectively for every single foreign key. I had a situation where we had groups of groups, and rather than having lots of linked tables, it was like, I'll just use an array, which was good until you realize you can't put a foreign key on that. And then you kind of sit and think, well, you don't really need constraints, do we? It'll be fine. And no, that was much more hassle than it was worth than just doing it the kind of old-fashioned way. So, with great power comes great responsibility. And I think another really cool situation where some of Postgres' data types really come in is kind of those unknown unknowns. And who here has ever heard of the entity attribute value model? At least 2 people. 3. And what's your experience with it? I'm betting pretty bad. And this was probably much more the old way of doing like this particular situation where you don't really know what you're storing up front and you need to support users putting arbitrary stuff in. Well, we've got a really good answer to this these days in my mind. It's called JSON-B. And so there's loads of times where, like, worked on an insurance quoting platform where we'd ask a whole bunch of questions, and the kind of product team and the UX people wanted to go and change all those questions to try and optimize stuff. And there was no way that we could have a situation where we'd have to make an application release every time they wanted to go and change or do an A/B test. So it was much easier just to throw the data in a JSON-B column, because all we really cared about at the end of the day was just being able to run a couple of operational reports off that data. We were not using that data particularly in any other way inside the database. So this was a really great, simple solution to a need to store all that data. I don't really know what it is, or maybe you're running like an API service and you've got letting your clients put metadata on your records. You can't control those situations, but what you need is just a way to kind of arbitrarily put data on. I think one of the interesting sides here is, you can also still control the shape of the data that you put in that JSON blob as well, right? So I've got a talk coming up at PostGIS online conference about like actually using schemas with JSON-B in Postgres. And it gets, again, right, we go into the doing analytics on it, and we can still go through and use that data, right? So the advantage of it being, especially as a, say, JSON-B, that's stored as basically a binary parsed representation of the JSON. We can still look up into that data. We can also do it with JSON that's just stored basically as text, but we can look up and we can access individual properties. And so, it's very easy then to go and do some of these reporting queries without, that kind of stuff. JSON-B gets even better because it plugs into the indexes as well, so you can actually index accelerate those key lookups if you actually want to use them in a where clause. So it's like, actually quite a lot of this is still very performant under the hood. And I think, another part of this and some of Postgres features is kind of when things go a little bit wrong. And a great example of this was a problem I had in a subscription application I built, where one thing we really didn't want is people to be able to have 2 concurrent subscriptions. But that's a situation that's not necessarily easiest to deal with, right? Because I want to have people to be able to have a subscription that's expired. You can have multiple expired subscriptions, but you can only have 1 active subscription. That's actually maybe, you could deal with that by having a history table or something. But Postgres, again, has a really, this is where like the partial indexes actually become really useful when we understand that we can also have a partial unique index. So we can have a unique index of active subscriptions where it's active as a status. So we can have as many in any other state as we want, but we can guarantee transactionally and ACID compliant that there is only ever 1 active subscription. That was a life changer in one particular application. It got us out a lot of problems. It's no fun having to refund people money. And then we got loads of features now for managing data. And whilst there's different use cases for this, such as just managing huge volumes of data or particularly managing lifetimes of data, I think it's actually more important to think about data lifetime when you approach data partitioning than it is like, I just need to deal with billions and billions of rows. You can have billions and billions of rows in a single table. There are some very crazy Postgres databases out there. But partitioning is very great for when you want to be able to manage that data. So if we think back to my original queue example, then we can actually, what we don't really want to do is keep stuff in there indefinitely. It's a very we only really care about what's current, and we want to expire stuff out fairly quickly. So this is where like Postgres and partitioning, again, becomes really cool and makes this really handy. So we can just declare that we're going to partition that table by the created timestamp of all of those rows. And then we just attach, and we can decide, based on the throughput of our particular application and use case, how short do we want those buckets? How, do we want to drop stuff every week, every month, etc. So, partitioning by month is probably the most common most people do. But now, like with declarative partitioning in Postgres, this is super easy. If anybody remembers the old-fashioned days of having to use table inheritance, this feature is now way much more usable than it ever was 5-10 years ago, when people used to say, we don't need partitioning, we have inheritance. Thankfully, they lost that argument. And the great thing here is to get rid of that old data, we just have to detach the partition, and then we can drop it. And if we particularly care about the data, we can archive it. We could even stick it in a different table space, right? If we manage our own server, we might have expensive SSDs, and we might have slow SATA disks that we can put the old data on. Partitioning to me is much more about like dealing with that lifetime of data. And then I want to move on much more into like solving problems with SQL. And I think there's loads of application developers out there that only really perceive Postgres in the database through the ORM they use. And in my experience, most ORMs don't let people use the actual power of the database. And from my perspective, right, the applications I've built have been a success because I leveraged these features of Postgres, and I helped Postgres solve my problems, rather than just treating it as a dumb data store. I'm just going to select data, and then I'm going to do the complicated processing in the application. Of course, there's always times we need to do that, but there's loads of times where if I push that kind of complicated part of my application into the database, then it can boost loads of different things, especially if you've got to deal with like the n+1 problem of lookups, or you've got complicated data structures. But there's also just so many things that's far easier to express in a single line of SQL than it is in hundreds of lines of application code. And I think the first place where this becomes really a big advantage is being able to pull all those different themes and concepts together. And this, to me, is where Postgres really shines the most. So, in that first kind of section about architecture, I introduced the concept of, like, say, text search and GIS information. I then introduced the concept of using arrays to do tags. Well, I worked on one situation where we had a text search of the index of our website, sorry. And we wanted to be able to do smart things, such as we had, it was a council website, so we had pages for each library in the county. And we knew that they were like service catalog pages. And we knew people's location through the HTML location API. We also knew the location that those pages were talking about. And this is where Postgres becomes naturally quite cool, in that I can now say, find me website pages about things that are near me, which is quite a cool concept that is actually very difficult to do in other platforms. And there are more complicated examples of this, but when you've got to bring all that data together from different kind of applications, doing it in your application becomes an absolute nightmare. And the biggest advantage of having it all in one place in Postgres is the ability to do this kind of stuff and not have to like shuffle pre-computed data back and forth between other platforms. And then we can get more complicated. And who here has kind of understands like hierarchical data, where if you've ever, say, worked on a video on demand catalog, then you end up with like a tree of trees. And there's loads of situations where you kind of want to then aggregate information right to the top. And the last thing you want to do is for like each record go and find all its children, then find all the children, and find all the children. Well, cool thing we do in Postgres is a recursive query. So this will go and traverse the whole tree for us in a single query. It's a bit mind-bending at times to get your kind of mind around what is going on. So first off, we have with queries or common table expressions. Who here uses common table expressions? More people, as I expected. So with these, we can apply a option on them called recursive, which kind of then turns that lookup into that kind of recursive search. So effectively use union as well to then self-reference onto the recursive CTE. So effectively, we take a starting point, and then for every row returned, we then effectively self-join again and do the query again until we kind of reach effectively everything, start the end condition. But this is like really cool for those situations where I need to traverse a lot of data that's all structured as a kind of tree fashion and aggregate stuff together. And then another kind of part on this kind of same vein is what are called lateral joins. So I think it's easier to think about these as a for loop for SQL. I think that tends to be a simpler way to explain it to a lot of people. But if we imagine situations where we need to go and for every row go and find some other information, and we can't do that just as a standard join because we need to basically rerun this query for every record in the kind of parent relation. So that's why I say it's more of a for loop, right? And lateral's a really easy way to do this. So it's amazing for doing stuff like funnel query type computation where you want to keep going down a series of like for people like marketing as they step through different processes, or just go and do like the top N of something. So if you want the highest CPU by load average, or if you want the top 5, right, this kind of approach, you just change the number you want in the top in that kind of setup. But again, very useful for those. It's not something you're going to use daily, right, but it's something that's really nice to know about that is there and available for you to use when you need it. And then, so for everybody who's used a CTE, have you ever used a writable CTE? Couple? So these are also very handy for those situations. I quite like it for, say, invoice processing, where I've got like a log of commission records, and then I can very quickly just go and say, right, in one query, find me all the records that fit into this month, sum them up, build the invoice, and then insert the invoice record. And in one single kind of query and transaction, I can go update all of those records, say they're assigned to an invoice, and create the invoice. So super handy for loads of this kind of stuff. Also quite handy for, say, like IoT type analytics and stuff. And then another cool little trick, generate series, is another one that I kind of go to time and time again for building nice displays of data and visualization. So, nothing really ever works 100% as you expect. So there's loads of times where you kind of have gaps in your data and things are missing. And generate series is great for being able to build that like x-axis of your graph, or where you want to make sure you have a bucket for every day of the month and stuff like that. You can do it across timestamps, you can do it across just standard integers, but super helpful. Basically, build your buckets and then just join your data into it where it exists, and really handy in pretty much every kind of analytical type reporting situation I've ever worked on. And then kind of in the same vein, I really like window functions. They're getting a bit old now. So they're not necessarily a new feature, but they are extremely handy for especially kind of reporting and analytical type situations. And just loads of times, like, so a really simple example here is, right, I want to just sum stuff up at different kind of intervals. And this is where we can start combining, like, other little utility functions like truncate a date to week granularity. So then I can have like a daily total combined with a weekly total combined with a monthly total, and kind of really easy to do this in SQL, be way more lines of code to do that in any application there. And then again, we can do the same kind of thing, but like using the kind of advanced extended window function syntax to do rolling windows. So you can do a moving average really easily. So if obviously the classic application for this is probably like stock ticker type stuff, but really easy to just do that kind of situation where you want to kind of do that rolling average across things. Or the other kind of one where I found the window functions super useful has been more of dealing with like counters. So in kind of a lot of IoT situations and say energy situations, we aren't reporting the usage during a period, we're reporting a ever-increasing counter. This is also the same in pretty much every kind of analytical situations like web server stats or server stats, that kind of stuff, like all those kind of metrics. In general, they increase, right? The kind of amount, the size of your disk increases, etc. You don't track how much it changed during that period, you track the size of it and it increases up. So to make it more useful to work out what actually the change was, you need to go and get the previous record. And this is where window functions are really handy. I can just use the lag window function, which will go and get the last record, which will tell me and work out what, I can then work out what the difference was and therefore what the consumption is. You can think of this effectively as differentiation, right? I've created the first differential of the actual value I'm tracking. And then we can wrap all of this up and bring it into a much more kind of complicated example where we want to deal with interpolation and missing data. So in a particular IoT type situation, we often misread, devices are offline, stuff's not there, we don't always get data sent in. So we end up with gaps. So we can start putting together all these kind of like bits I've been introducing to kind of solve a much more complicated problem that's actually then quite difficult to go and reprocess in the application as well. So what we want to go and do is work out all of the days we want data for. So we're going to use generate series as a nice way to do that. We're going to go and grab our metadata as the first part. So now we have all the time buckets we need with all the data we have, and where we haven't got data, we'll have a null value. Now, computing in a linear interpolation mathematically is not that difficult, right? We just need to know the last value we had, the next value we have, then the time difference between the two, and the difference between the two values we can work out and generate the values in the middle. So that's quite easy. With window functions, we can use window functions to go and grab the last values. And then we just do the very basic maths. Now, so this is kind of like how we go and get that data. Now, anybody who uses window functions very much, does this window function exist? Does anybody use window functions much? Yes, there is last value, but last value doesn't do exactly what we need because it gets you the last value in the window. Whereas we need the last sample, effectively. We know that, so we want the last known sample, which isn't a built-in window function. Huh? Yeah, kind of. But what we can do in Postgres is define our own aggregates. So we can define our own aggregate functions, and then we can make all this work. So, and effectively, we can define aggregate functions in any of the procedural languages that exist. SQL is slightly simpler if you can, more efficient if you can use it. And effectively, the way it kind of works internally is there's a state that you can declare, and then there's a function that applies the transition from for each record it gets that's not null, it then mutates the state. And in this particular case, all we want to do is just select the last value you've got, which is really simple. We just select the second argument, which is the new value. And that basically creates us a very simple sample and hold kind of thing that then makes this all work. And that is the end of the line and the end of my talk. So I hope it was interesting. And are there any questions?
Does anybody have any questions?
Yeah, just in case you remember, if it's possible to define TTL for partitions, so they get out-dropped after some time.
Not in core Postgres, but there is a extension called Partman, Partition Manager, which does all that kind of stuff. So you can specify, I think Partman can do, it can definitely do partition creation. I don't know off the top of my head if it does partition deletion, but I'd assume if it does partition creation, it probably can handle with partition detaching and stuff like that. Obviously, like if you're a super high transaction volume, then dealing with dropping and detaching partitions and creating partitions can be a problem. But Adyen have done a couple of good talks on that particular problem, right? If you're dealing with hundreds of thousands of transactions a second type stuff. Anyone else?
Thank you for the presentation and the nice sticker on the laptop. I love the tourist routers as well.
Oh, right, yes. Good old FOSDEM. And also the Czech CZ, right? CZ Nick, right?
I wanted to ask, how do you version the code that you put into the database and make sure that it's up to date?
Yeah, schema management is an interesting one because it's a big topic that nobody ever really talks about. So a couple of these databases I've worked on had like 1,000+ stored procedures with a couple of them, and managing those kind of schemas was troublesome. I think the big mistake most people do is the common approach is like patch files. So you never really know what the current state of play is. So I personally think that's a bit of an anti-pattern, although the fact that pretty much everybody does it. What I tend to do is every entity I have in the database has a single file in Git. So I have a folder for every schema, then a folder for like different entity types. Then I have a bash script that just goes through them all, concatenates it together into the schema. And then migrations, I use a PostgreSQL function to apply them only once. By just having a table, you check if the migration's been run or not, and then run it if it's not been. The great thing with Postgres, DDL is completely transactional. They've even fixed enum these days. There's a couple of things that aren't, but so you can do all the whole thing inside a single transaction as well. So your updates either apply or don't. And if you work on kind of big databases as well, I think the advantage for like writing migrations manually like that is because if you do things like add a column and you don't fully appreciate what you're doing, you lock that table and cause huge havoc. So I think there's a lot to be said for having a framework that takes a little bit more care about writing those migrations rather than just using, Liquibase or whatever the current thing is. But yeah, that's kind of how I tend to do it. My little bash script is actually on my GitLab page somewhere for that. It's on my kind of personal website and also on my company website. I think was another question.
I have a related question. You say that you don't like ORMs. I totally agree with that. But how do you interact with the database from your application? Use data mapper or some other approach, some other style?
Yeah, I guess it's kind of unfair to say like don't use ORMs. Nobody's going to really kind of follow that. I think there are some ORMs that are easier to use than others at letting you write your own SQL. To be honest, it's also most of my own applications and quite a few of them I've worked on. We've never had the application directly write SQL. So every interaction between the application and the database was through a function. So every single query that was available for the application was a function in a like API schema inside the database, so that we could, and actually had some kind of cool benefits in that. The great thing there is you can transactionally apply the changes to those functions. So the database team can move stuff under the hood without the application team knowing about what's going on. So that's kind of been how I've personally done it. And then I find it's a lot easier to just generate the binding code from the database for those kind of situations. Or kind of like sometimes, just manually write the bindings to those kind of functions. But that's kind of how I tend to do it, has been we effectively have a function for every kind of query we're going to run. And it also means you end up with a very controlled interface between your application and your database. Makes it a lot easier to update and pull stuff. Any other questions?
I would like to say if you're using Go, SQLC is a really cool library where you can write your SQL queries and stuff, and then it'll generate Go code for you, which is like the opposite of an ORM, which is pretty cool.
Yeah. Yeah, I mean, I think a lot of people, it's not that difficult to, just generate it from the database backwards more often than not and things like that. I think also the number of things that people kind of do wrong is they try to see, all their model objects need to be one thing in the database and stuff like that. And then often, how you want to structure your application model objects isn't necessarily how you want a data model your database. And so don't fall into that trap if they have to be the same.
You talk about really sophisticated things, and from my practice,
Yep.
I see that it will be a lot of troubles in supporting this in future. And I think you mainly talking about some application development when you have dedicated database team that actually doing everything by themselves and holding these changes by themselves. And because really from my experience, every time when you come to some project when 5-10 years ago someone very smart do this stuff, it's always disaster. It's really disaster. Nobody knows what's inside. It's not in code changes, not in Git history, some triggers inside Postgre, something, some magic happening. Nobody knows. And Postgre now is, everyone is JavaScript, Angular stuff, and nobody knows what to do.
Yep. I think there's two sides to that, right? I think in many ways it's far too acceptable for developers to be considered good if the only thing they know is their language. My argument would be if your developers only know one language, they're crap. And you should hire some better developers. But more importantly, right, it should be considered to be good at your job, you should know how other things work in your stack. And there's so many times where if you don't know how networking works, all that kind of stuff, you can't, as an application dev, you can't just stay in your little box. So yeah, of course, is again that with great responsibility, with great power comes great responsibility problem. But also I think it's getting your team out of that mindset of that they can't go and learn other things is a big kind of thing you have to push for and try and get people to do. Also, it's a trade-off, right? I'd much prefer to maintain a 2-line SQL statement rather than 10, 20 lines of code that's basically just doing a group by, which I've seen other teams do, right? Especially JavaScript people. Or select a whole table out and then do .filter, right? It's clearly just people being lazy and not knowing what they're doing, and just kind of challenging people on that's not really acceptable at times is kind of more what's needed. And just push for being slightly better. But yeah, of course, right, not every team there's only been probably 2 projects I've worked on where we had a dedicated database team. The other kind of projects I've worked on, it was more maybe me as the lead dev who was pushing the database side. And yeah, look, don't get me wrong, on my current project right now, a bunch of people are coming kicking and screaming, right? But at the same time, they're actually learning and getting better. So sometimes, you just have to put up with them arguing a little bit, and then after a few months they stop because they start seeing the benefits themselves. But yeah, it's that social side of coding as well, right?
Okay. Thank you. Not a question per se, rather a remark for your presentation. I think most of those subjects should be directed to non-database programmers.
Yes.
Because those subjects, so advices, shown that a lot of tasks might be realized better and more effective during those operations in database, comparing to the, let's say, iterative approach in applications.
Yep, indeed, right? I mean, this talk, as I kind of said fairly early on, is much more designed and geared towards application developers, really. But yeah.
What about caching? Do you use Postgres in a way that you don't need it, or what is your approach to that?
I mean, there's always times and situations where you need it, right? But I think also, like, I've worked with so many teams and applications where people just cached everything, right? They stuck the cache in front of every single database query. There was no intelligence, there was no decision going on. And there was one project I worked on where we were sticking like everything in, I think it was Membase or something. It was like one of the weird sort of versions of Redis before Redis became super popular. And I pointed out to people that actually the reads from it are slower than just the read workload from Postgres. You do some performance tests, right? And actually, right, it's, you know, the main cost there is actually just serializing stuff and sending it over the network for a lot of those simple lookup by key stuff. So if it's simple queries like looking up by key, in general, you don't need to cache it, right? Cache work, don't cache results, I think is the key thing I'd say. And often you're better off probably just sticking HTTP cache on your application in lots of cases. Obviously, there are situations where maybe you kind of got key state you want to keep cached, and you know, maybe like you got like a total of everything done today or something like that. Makes much more sense to kind of store those roll-ups. But then also flip side, sometimes when you want to do that, you also need that to be asset compliant, so you might be better off putting it in Postgres anyway. But I think that's the key thing, right? Don't prematurely optimize your code. Do caching when you need it, and cache actual work and processing. Don't just cache because it's slightly quicker than Postgres. Because you'll find out, you know, it's actually quite easy to rescale Postgres, right? If your problem's mainly read-only, then you've got a nice, easy life, to be honest.
Everything's fun until you run out of memory.
Yeah.
Okay, any more questions? Nope. All right. Thanks, Chris. That was pretty cool. And there will be a short break, and we'll be back soon. So, welcome back. And we're going to have Alessia telling us about full text search. So, take it away.
Okay, thank you. First of all, thank you, Chris, for the nice presentation. I think I can skip it to the last slide because there's nothing more I would say, because all the technologies were mentioned, including the composability of the components together, so no surprises from these slides. But let's give it a try. We are running some back office or CRM application which is used to manage clients' records data, and we have some typical data, username, email, client addresses and stuff like that. For sure, the team needs to search the data, so what happens? Good. Bit button. So we have clever functions with 10 to 20 arguments just to search a given table for the particular column and filter the result set, which is amazing because it surprisingly works. And yes, it's 18 years old, most probably. So the task was just to implement something more versatile or universal for the customers. The data presentation is quite typical 19th application. So you have filtered view and you can show the details for the given record. So enjoy the modern design. And the request was quite easy. Give us something new, modern, and easy for customers, for the end users, sorry, not for customers. So the people want just to put a search phrase into a field and get the results. Since we are implementing it at the database level and it integrates in with existing applications, the database is not responsible for forming the complete records for the results. It just provides the IDs, and it's the responsibility for the application to load all the details which needs to be displayed on various screens. So the result set is just a set of IDs, and the application handle all the details how to present it to the end user. What do we need? We need some tools to work with the data, and we need some documents to be searched. So these two major components builds up all the magic. Now the full text search tools provides various features. We can search words, phrases, and the key is we are searching a document for words and phrases. Typical use cases are email archive or a website with a set of articles which can be searched and returned to the user, which is completely opposite to the design of having customer data in several tables. So we do not enjoy the document title and assigning different weights to document titles or chapter titles. But on the other hand, there are some other features. Postgres has a rich support for language-specific features. For the full text search, there are predefined dictionaries, and you can define your own dictionaries. Trust me, it's very easy because I've just opened the manual and built the dictionary for the Polish language, just following the manual. It's not in the slides because I just run step by step and build it, so it was very easy. Funny fact is that in the end we haven't used it. Well, it supports gender inflection, looking for the word root. If you are producing the results directly from the database, you can highlight the results. And we do have operators to be applied on the search phrase. We have index support, already mentioned, thank you. So we can speed up the search, and we have functions to work with the search because you've already heard a magic word name of the data type which is used. So let's dive in a bit. First of all, key tool is a parser which gets the document in and parse it to tokens and classify the tokens. So it can be an ordinary word, it can be email address, number, hyphenated word. Depending on the parser configuration, you can limit the set of tokens which are recognized and classified by the parser. You can use predefined dictionaries or create your own dictionaries in order to support language-specific features you need. For example, the gender inflection is language-specific feature. As was already mentioned, the text document is parsed to something which is not a truly binary, but think of it that way. It's a special data type called TS vector, which stands for text search vector. And the phrase we use to search is compiled to TS query. And these two creates a complement, so we can use a TS query to search TS vector data. And we have the match operator, which was already mentioned. And this match operator gives us the ability to compare the TS vector together with the TS query. Fortunately, we can use the indexes. There are some more operators like and or not, what you expect. The less typical operator is the distance. So you can say there might be a word Prague, some specific amount of word distant from the country name, potentially, if we want an example. We can use brackets, and we can use for start of the word if it applies. Good example is the Postgres manual, so I haven't done any attempt to rewrite it. We might have a table, and we just simply concatenate several columns of a table to build a document. Or we might join multiple tables to build a document. That's the key, because this is typical for the application. We have a client table with client addresses and some comments to the user, to the client. So we are dealing with multiple tables, and we need to process them in order to implement the text search. What we do need, the document already mentioned. Single table contains the root data when the client record is created, and there are several tables referencing the parent record using various data types. Text, definitely date for various fields like birth date, license, driving, validity, registration date, whatever you imagine. And there are some labels like status or whatever, so the user might have a lot of labels attached to its account in different contexts, and for sure there are some Boolean columns. Now, probably you have already faced the case that you're requested to implement something which is written in a ticket, so you do your best to implement it, and suddenly you realize the users expected something completely different than what they requested. In this case, it means that please let us write a phrase, apply whatever human or artificial intelligence to understand what we do really want instead of what we write to the query and give us those records. Sorry, this was not implemented in the end, and I'll show you why. That's not difficult to guess. So this implements a simple search, no vectors, no artificial intelligence, just searching the data we do have in the database. I did some attempt to translate it, but sorry, the pictures are not translated, hopefully clear to understand. So we have some, let's say, example, a basic client table, a table containing client addresses, client nodes, and somewhat where we need to compile a document from all these tables. We can imagine some scenario that we will create a function that reads all the involved tables, pick up the columns we need, and creates a record in full text search table where there will be a separate record containing the TS vector, because we need to store the data in TS vector format to be able to index it and search efficient way. Probably this is not the best design, but I think it could work. To make it more clear for us, we decided, well, the TS vector document is good, but if we want to debug it, it's hard to read it. JSON-B is a format which is better, as I have learned in the PGConf Berlin. The B stands for better, so that's a clear reason why to use this data type. What's important is that we've decided that the JSON document inside will have a table name as a key and the columns and its values as a data under the key. So the path within the JSON is very simple, a table name and the table data. So we can debug it very easily if we want to know why a certain record was matched, which would be quite difficult from the TS vector. Just to get some overview, the parent table contains the client record, and the full text search table is simply referencing the client table, having a foreign key, and the important point is that it's on delete cascade, so as soon as the root client record is deleted, the full text search record is deleted as well, and we need some triggers to put it together. As Chris mentioned, it's all composable and we can pull multiple technologies together. So, nice function, we can use generated column. Great feature. We don't have to write a trigger to keep the data up to date. That's famous. And moreover, there is a prepared function JSON-B to TS vector. So we don't have to tackle with parsing all the JSON-B components because there is a function for us. That's the reason why we might put all the source data into a JSON-B document, which is, let's say, our blueprint, and transform it into TS vector by generated column. Note that we using some custom dictionary configuration. This is the column, and this is the filter which tells us what data types should we see in the TS vector data. In this case, these are string and numeric values, but it's possible to define we want to include the JSON keys. There will be multiple redundant values, so it is not good for our case, but that's possible if you need it. and it's stored because we need the data to be physically exist in the database, and therefore the data might be indexed. And for sure, one of the filters could be all, so everything from the JSON is indexed. So there is some kind of prototype. We have after insert trigger, which creates the full text search record, and some after update trigger, which keeps the record up to date. Great. Or not at all. If you take a look at this, we have a function that looks up a lot of source tables, regardless what table data has been changed. So it's so many lookups. And now the question, well, it's good to have for debugging the JSONB column, but on the other hand, it costs you some disk space. Well, in fact, disk space is pretty cheap nowadays. But since we are entering, or we already are in the cloud era, the IOPS are expensive. So probably this approach needs some tuning or development to spend less I/O on collecting all the data. Still keeping the general idea, we might have a trigger, a generic function, so the triggers will fire the function, it grabs the data, builds the JSON, we have all it together. Good, still the I/O intensive scenario. On the other hand, we might think that we'll create per source table or source entity dedicated function which builds a JSON consisting of the data from the given table or from the given entity. So we might have for the base table a dedicated function, and for addresses another dedicated function. In case we are updating a single table, the other tables are untouched, so we do not need to read the data, we do not need to process the data, so we save some CPU cycles. And all what we need is to find a way how to update the JSON with just a partial data. To do that, we have some simple trigger. This is the parent table, the client table. So the pass within the JSON is just consists from the table schema and the table name. And the data is very simple. We just call the JSON build object, and we call a function that returns all the data we need from the client's table, just insert it into the full text search table. Trivial thing. The document function is, again, very simple thing. Select several columns from the table we want to read the data. Just do some sanity checks. So first we convert the row into a JSON, which is a nice function because it preserves for us the column names as the keys. We strip the nulls, and as a fallback, it's an empty JSON in case of all the values will be nullable and deleted. This is just to have a generic function. The update trigger is slightly more complicated, but it's the trick which saves a lot of time. Still, we need the table key as a pass to the JSON, and if a given table row selected columns has changed, we simply select the full text search table for the document, and the document table is updated using the JSONB lex function. As an input argument is the original JSON, and what we can do defining the pass, so we know which top level key will be updated, or any generic pass, but in our case it's a single level. And the replacement is just collected from the same function which is responsible to collect the data for the inserts. So we are reusing it. And now it's the trick, create if missing. So if a key for a given table is missing, the new part of the JSON is created, as well as if it has been deleted, we remove the key from the JSON, so we are keeping the JSON up to date. Few more examples. If we look at some table referencing the client table, we create a trigger. Now it's an insert update delete trigger because we already have the row in the full text search table. And we can simply collect the data we want to insert, just using the document function related to the table for the client comments in this case. And the implementation is almost the same. Just get the path, the ID of the client, the replacement we want to do, and we apply the same function in the same method. So we've reapplied the same pattern multiple times. We have dedicated functions for each table or for each entity we are grabbing data. This mitigates the necessity to collect the data from multiple tables and building the whole JSON all the time, because we might update its particular piece of the JSON or particular subobject within the JSON. And this is just an example. If you have some multiplicities, you can use JSONB aggregate. For example, if the tags wouldn't be in an array, but it would be relational rows stored, so you can use JSONB aggregate and create an array as a part of the JSON, and it's properly transferred using the function JSONB to TS vector. It's properly parsed, so that's a great enhancement. That way, we have built the document and we are keeping it up to date. Very easy. What we do need, as already mentioned, some index to speed up the search. Why the gen index? Because it was in the manual and it works. I haven't investigated it more because it just works. Well, now we need to search the documents. So we have the match operator, similar to what was already mentioned. We are using functions to let the application access the data. So we have a function that implements the text search, single argument, the TS query, and it applies the search on top of the TS vector. It's very easy. Bear in mind, it must be already normalized. So the TS query is somewhat, let's say, machine kind of language or structure, despite it's not binary, but still think of it that way. The underlining function is very easy. You can just call the function tsQuery and just provide some term you want to put in. This is example of the let's say plain text representation which might be transferred to the tsQuery. Probably users are not about to write this kind of queries, but could it be? So we've implemented several, let's say, interface functions. The first one is to convert the plain text to tsQuery, like in the what I used in the previous slides. What it does, it processes all the stop words defined by the given dictionary, provides the normalization, and it automatically applies the AND operator between all of the words which are provided by the user within the search phrase. So finally, it looks like that way. We can see the normalization in the end. More advanced function is a phrase to tsQuery, almost just like the plain text to tsQuery, but it keeps track of the distance between the elements. So we might see that it will transforms into the same words, but keeping the distance parameter or putting the distance into the search query. So the word order and their distance is relevant for the search. Postgres also provides a function which tries to mimic the web search interface, so we can give users to use something that is similar to web search engines, and the syntax is almost similar, so we might exclude some words which is translated to tsQuery, as you can see. And yes, there is a function just to use a search text to tsQuery using the plain syntax, so we potentially allow users to use this advanced syntax. I can't imagine any user doing so, but it's there because it was very cheap to implement. And it's up to the front-end team which function will be implemented and how they let the users decide their favorite input. But since we do have the composability, all of these functions producing TS query, so we can use a single function for all the parsed sources to perform the search on top of the data. And as we've seen, it's very simple, just applying the match operator, and that's it. So Postgres makes it for us very easy. So we do have a full text search, we do have the document. Do we want something more? Probably if you type a query into, or if you are writing a phrase to Google or any other search engine, you want to see how many results is expected. Well, it is an estimate. Can we do it in Postgres? Anyone can execute a query. Potentially, if you type 3 letters, it will return almost all the database. So first of all, it will take ages to execute the query. If multiple users do it simultaneously, you will overload the server and it will take ages. So there is a better solution. Postgres is able to show you how a given query will be internally processed by Postgres, and part of the result is expected amount of rows. This is based on statistics, which are collected manually or by the auto vacuum for all the tables. We can use the explain, which is very fast because it simply parses the query, reads the statistics from the table, and it does not touch the table underlying. So the explain is extremely fast, and we can parse the result from the explain. 3 or 4 versions in the past, the output of the result was enhanced for the possibility to use a JSON format for the result. So it makes it from text search parsing to just reading from the JSON, and Laurens Alba from Cybertech give some good example on the internet. So I've grabbed it and use it almost just as Laurens wrote it. So it's very easy. We have the query, which is somewhat there, just providing the user phrase, which is putting the phrase into the query provided by the user. We are executing the explain the query. We want the JSON format for the output, and the output is an array of JSON, and the first one, which is indexed at 0, gives us expected amount of rows. So it's a millisecond operation to give the user an estimated overview how many matching records are expected, and it works great. So the same way we pass the queries, we reuse the same functions because the result is TS query, and we use the TS query to another function, which is a tool that provides the application an ability to give a user estimate, and all the asynchronous processing of web pages, I know nothing about the details, can just update the amount of rows to the user as long as the user is typing the query. So that's a great thing, I do believe at least. Still, are we done with the full text search, documents, tools, estimated rows? No, we can add one more thing. Honestly, this was not implemented because it wasn't requested by these users, but we've done some testing and I'd like to share it with you. There is a function called tstat, which gets to SQL query and provides some statistics on underlining full text search data, especially the word, the number of documents where the word occurs, and total number of entries where it is available. An example, again, it's just copied from the documentation. How it works, if we issue the query, I've just limited this to have it fast, so we can see the word, number of documents, and number of entries. So if we want to implement autocomplete, we might use this tstat function just to build a dictionary and all the web tools can use it on behind the client as it types the word and look for similarities. Why I mentioned trigrams? Because trigrams are a very good tool for fuzzy text searching. This is the first topic that hasn't been already mentioned. Good, at least one good point. So you can use trigrams to do a fuzzy search and just sort it by similarity and decide whether you want to show it to the user and offer some autocomplete. Another possible implementation is used unnest function on the TS vector data, but it's per row, so you have to probably do some insert on conflict, do nothing, just to keep track of unique amount of the words, not amount, about getting the unique dictionary of the words which are relevant to the full text search. And yes, that's it. Thank you.
Cool, thank you for the talk. That was really cool. Does anybody have any questions? No questions, really? Does everybody know everything about full text search?
With the trigrams, how do you prevent if you type a longer sentence that the fuzziness doesn't just give you something, because like you have so many trigrams at that point that basically anything matches a certain.
It does not solve sentences. Yes, it doesn't work for the comments. It doesn't find a sentence. So it's up to the front-end application to keep the track of characters user is writing until the first space or hyphen or whatever else, and just providing the single word. That's not that good as Google.
Yeah. Actually, I know answers, but it's interesting to let others to learn something. So actually, two things. First, how we did paging or about paging, how we resolved that, or actually we not, but how we argued against that. And second thing, which was in requirement to make this search able to find records by exact by exact values, like amount of money recorded or time ranges, etc.
Well, good point. First of all, one of the discrepancies between what was requested and what was intended to receive was the artificial or human intelligence behind. So they wanted just to return single row or 10,000 rows. So it should be a reporting tool together with a full text search. Well, I do not believe more than 3 screens can be browsed by a human, so it makes sense just to limit the amount of rows. The second thing is we are using the similarity the similarity distance. I think it's a Levenstein similarity which is used behind. So the most matching rows are sorted first, and it's limited. I don't know how it was implemented at the front end, but one of the reasons why to implement the estimate function was just not to allow the user just to execute the search if it returns 10,000 rows. Well, 100 or 20 rows or 50 rows, we might argue what is reasonable, but definitely not 1,000, so it's not a reporting tool. And the key point I've missed to comment on the slide is the topic of different dates, statuses, and Boolean flags. Finally, there was a birth date only, and all the other dates needs to be searched different ways because the full text search has no chance to recognize the context. Thank you for the question.
Any other questions?
It's not a question, just a tip for you and others. Postgres full text search supports also waits, and it makes sense to set a higher height, higher weight to things like name, surname, and lower to nodes or some sentences.
Yes.
I'm very surprised that this works for you, because I've implemented full text search in 2 projects, and it didn't really work well without fiddling with weights. And yeah, and second, I just remembered second point. It's not really necessary to build single TS vector. You can just contact multiple TS vectors on the fly. It works pretty well and faster than one would expect.
You can concatenate TS vectors, but still you need probably to have them indexed, or you are searching 3 TS vectors.
Yes, but you can have multiple TS vectors. For example, you had 3 tables, so one per each table, and each index it. And yeah, it's probably not so efficient when you search all 3, but that depends on the situation. In the project I work on, there wasn't some serious penalty in performance, and yeah, I think that is so possible to build single index on multiple TS vectors, but I really don't remember details.
If you have it in 3 columns, it's just a function-based index.
Yeah.
I have to know that a few things surprised me. First of all, because I'm fan of anything I can learn, the weights was one of the things I've tried to promote it, but from the user testing experience, it was not welcomed. They want to have it all the equal way. But since we do have a dedicated functions per document, it's very easy to add the weights there. As well, having those functions, it's very easy to regenerate the full text search table, because we can just apply the function and collect all the data. So if it will be requested, we can do so. Yeah.
It's most valuable when you have mix of single values like name, surname, like this data, and sentences. Because when you contact all of these, then name of the person have the same weight as some word in the node.
Yeah, that is absolutely clear. But as I mentioned, users surprised me. They didn't want that feature. And they were not satisfied with some prototypes implementing this feature. As well as finally, it serves mostly Polish language records, but finally the users were most happier when we just combined the English dictionary and an-accent dictionary, because gender inflex and the other features cost returning unwanted records. So it was a surprise for me. That's why I've built all the Polish dictionary, and later it was discarded.
And you mentioned user experience, and it's a very interesting question in search always, in every project. And how did you measure it? I mean, you know, it's how you adjust search results for users. Did you like record some statistic about what user ask and what you return? Something like this, or is just verbal?
I just simply implemented several prototypes and discussed it with the users. What is more expected, especially at the ordering and the matching, like the gender inflection and the other stuff. So it was just a questionnaire, but not formalized, and it's not based on statistics. We've just implemented several proposals, explained why it returns those rows, that they are matching based on what the rows are matching, and the users give us the response what they are expecting, and that was how we built it.
How many users and actually data sets you have? Like it's millions, thousands, hundreds?
Tens.
Oh.
Not a big sample.
Okay, thanks.
Any other questions? Why do you have to sit on the other side of the room?
May you walk. Really good talk. There's a lot I didn't know actually as well. Did you play much with ranking algorithms? Because I think for me that's been the thing people have complained about the most. Of like, there's kind of two really, and it doesn't always necessarily do what people perceive they want. And what's your experience of that?
I think I can say why people wanted it without ranking.
Easy then.
But definitely the technology is there and it's very easy to add it, yeah.
Anyone else?
What is your operational experience with the application now? Did it add considerable resource consumption, or can you add a few words about that?
Well, as a DBA, I can say I do not see any extreme workload on the database, and honestly, I'm not checking how much it's being used in practice. As long as a function is not overloading the database, it doesn't point my interest. So I don't know.
Were there considered alternative solutions?
Yes, we've been challenged with the Elastic and other stuff. Surprisingly, Postgres wins.
Okay, anyone else? I guess not. Okay, well, thank you for your talk. That was really cool.
Thank you.
Pretty sure we all learned something. Thank you to both our speakers. We had something to learn today. And yeah, now we party.